Okay, so let's start with this third lecture of the System Man and Cybernetics Society Italy Chapter. I'm Graziana Cavone, the secretary of the chapter, the Italian chapter. As you know, the IEEE is a non-profit organization and is also devoted to the advancement of technology for the benefit of humanity. The System Man and Cybernetics Society is one, of course, of the Society of IEEE. It has more than 1,000 members up to January 2026, and it publishes 7 journals and magazines. And it is a really unique society since it combines different types of research areas that are the system science and engineering, the human-machine systems, and cybernetics. Being a member of System Man and Cybernetics Society provides to the members a lot of benefits, in particular knowledge, since it is possible to have access to magazines and SMC e-newsletters, as well to the IEEE Explore digital library with all the publication of the society. It is possible to be part of a community, so participate to various interesting events that allow the members to connect and create relationships and networking in the scientific field. It is also important for the profession. It allows to participate to awards and also scholarship scores, and there is also a job site. Of course, being a member of IEEE has its own fee that is differentiated depending on the country and the level of membership. But being a member of the SMC Society is not so expensive. For the members, the cost is just $9, while for students, it is just $1. As for the activities of our Italian chapter, since a couple of years, we have built up this award that is the Early Career Researcher Award. It is recognized to young researchers, so at the beginning of their academic career. During the last year, the award was provided to Dr. Claudio Savaglio during the event Automatica.it 2025, and he provided a talk on IoT Continuum and Smart Healthcare, the ENTRAS project. Be connected to our website and also our social media, since all these activities are always publicized, and all members, of course, can participate and take the chance to participate to these kind of events and calls. As for the main conference of the SMC Society, it will be in Bellevue, US from the 4th to the 7th of October 2026. There is still time for the submission of special session and regular papers up to 19th of April 2026, and also work in progress and industry paper submission on the 3rd of May 2026. Another important conference is the IEEE Human Machine Systems 2026. It will be in Singapore from the 1st to the 3rd of July 2026. Unfortunately, the deadline is already passed for the submission to this conference. We also sponsorship another important conference that will be this year in Rende, Italy. That is the IEEE Smart World Congress 2026. And the deadline for the submission of full papers is the 1st of April. Then we have also the IEEE Cyber Humanities Conference that will be in Venice this year from the 7th to the 9th of September 2026. The deadline for the submission of papers will be the 10th of April 2026, while the deadline for workshop and proposal has already passed. And let's move on with the events and lectures that we propose as the SMC Italy chapter. In particular, today we will have with us Professor Stefano Panzieri, but as you see, almost every month, in particular every last Friday of the month, we will have a lecture on topics related to the SMC Italy chapter and society. And there will also be the SMC Day from the 2nd to the 4th of September. There will be a conference in Italy that is again Automatica.it, where we will have a dedicated special session with all a specific topic and all papers related to the SMC society. So let's welcome now Professor Stefano Panzieri from Roma University. He will provide a talk on iterative learning control principles, methods, and emerging trends. Stefano Panzieri is a professor of automatic control, as I said, at Roma University. He is a real expert in the automatic field, especially of iterative learning control, robotics, distributed estimation, and critical infrastructures. He is really well known in the field for his publications regarding cybersecurity, especially in industrial automation and complex infrastructures. So welcome, Professor Stefano Panzieri, and now the floor is yours.
Thank you very much. Thank you very much. I have to say thank you to Laura Gerrè and Graziana Cavone for this invitation. Was really appreciated because I had the opportunity to remember something that happened many years ago at the very beginning of my career, because I started with iterative learning control. Also, my doctoral thesis was on this topic that I continue to follow in the years, and I try to apply every time I can. Okay, but let me share my slides. Okay. Okay, I must say that there are more than 40 years of history of this topic. So it is clearly impossible to make a survey in 1 hour, including every application, everything that has been done in this field. And maybe one thing that I have to say that maybe we were doing almost data-driven control, but we didn't know, because with iterative learning control, you work with data. You build your control starting from acquisition from the field, from the system. But if you ask me, iterative learning control is really a data-driven scheme, well, I have to say sometimes yes, sometimes no, because in many cases, as is written here, the model is required. While we know that in data-driven schemes, you try to avoid building your model, and you just want to build your control starting from raw data coming from the system. But we have to see something later. Okay, for people that absolutely don't know what is iterative learning control, you have to imagine that you get a system. Maybe you also already have a controller that more or less is working, and you imagine that you can repeat several times your experiment, your trajectory, and that each time you repeat it, you add a contribution to your controller that is calculated starting from data collected from previous iterations. Okay. So the two principles is that the system is reinitialized at each iteration and that the control is updated. So you need a memory, of course. This is a very easy scheme, and but the problem is when such approach can converge, and which is the perfect law to update your memory and to update your controller. Well, I think that we must go back now at the very beginning. And at the very beginning is 1984, 40 years ago. 1984, there was a professor, a Japanese professor, Professor Suguro Arimoto, that started showing us in a small article, Bettering Operation of Robots by Learning, that very simple law, the one that you see now, in which the next input or the next additive term is calculated by simply considering the previous iteration and adding a term that depends only on the derivative of the error at the previous iteration, it is sufficient to get zero error after a certain time. This is called a D-type algorithm, the derivative type algorithm. It is not strange that we consider the derivative of the error in this feedback, because you have to remember that in iterative learning control, you reinitialize the system always in the same position. So the error at t equal to 0 is always 0. And of course, intuitively also, if the derivative of the error is always 0, okay, also the error will be 0. This is very intuitive, but you have to demonstrate that everything is working. And the demonstration in this case is quite simple. It's quite simple. There are only two hypotheses. The first one is that the product C multiplied B, okay, you're supposed to have a linear plant represented by A, B, C, D matrices. The product CB must be full rank, and this means that the relative degree is equal to 1. So no input-output delay. This is a quite restrictive hypothesis, of course, but this was also the very first paper on this topic. We will see later that the relative degree is very important in such algorithms. But why the relative degree must be 1? Because don't forget that you are updating the input at time t with the error at time t. So you suppose that in some way the error at time t has an effect on the output at time t. So you must have a relative degree equal to 1, otherwise you cannot do. Then the demonstration is very easy because you have just to calculate the output with the well-known relation. This is the free evolution and this is the forced response. And then you have to calculate the evolution of the error. So E dot, the derivative of the error at iteration k plus 1, that will be given by the difference between the decided output, the derivative of the decided output minus the derivative of the output at iteration k plus 1. Then you simply write all the equations that give y dot k plus 1. You have a lot of calculation here to do, but they are only derivatives. And at the very end, you have an expression like that. Now, you can try to make the norm, to take the norm of this expression. You can use a lambda norm and also an infinity norm. And it is almost easy to understand that considering a sufficiently large lambda, it is possible to bound all the terms in the previous expression. You have to work a little bit, but not too much. And so you can reach an equation in which there is on the left the lambda norm of E dot k plus 1, and on the right the lambda norm of E dot k multiplied by a parameter rho that can be made less than 1. So this is a contraction map, of course, and this implies the convergence of E dot. If E dot converges, of course, also the output will converge. Now, this is really the very first algorithm that was presented. but it is an important one because all the subsequent algorithms that we will find are more or less based on such demonstration. Which is the main problem of this approach? The main problem is that when you go to consider, for example, a robotic system, in which you have a state that is composed by position and velocities, if you consider as output all the state of the robot, when you go to do the derivative, you got the accelerations. And in any case, even if you have a state that is composed, for example, only by variables that are positions, when you take the derivative, the risk is that you go to accentuate the effect of any noise that you may have on the output. So taking the derivative is not always the best thing to do when you are controlling a real plant, of course. To do that, to cope with this problem, other ways of updating the memory have been proposed, and one of these, always due to Arimoto, together with Kawamura and Miyazaki, the three people that mostly worked in Japan. In that period, in 1985, they proposed this kind of update in which you can see there is the error and not the derivative of the error. Well, unfortunately, the convergence using the error and not the derivative of the error is not easy. But they demonstrated that if the system is strictly positive, linear, time invariant, that is, the passivity conditions holds, and this may be true, of course, in many cases, but not always. Okay, if you have this passivity condition satisfied, okay, you may have a convergence to zero. Now, this is of course good. And later, Arimoto, with the other people that we saw before, proposed also more general laws. This is something that can be considered a PID controller in the iterative scheme, in which you have a feedback from the error, from the derivative of the error, and also from the integral of the error. Of course, according to the terms that you put inside your update, you have different conditions that you have to satisfy to have convergence. After that, we can find other approaches, of course. For example, Togai and Yamano, always in 1985, 84 and 85 were very prolific years for this control scheme. They proposed something starting from the hypothesis that the system is expressed as a discrete system. So that can be also time variant. You see that the matrices A, B are dependent on the iteration. Sorry, on the sampling time. Okay. As an update, they have to consider something a little bit different. They can use, of course, the error. Look, U, that is the input, is updated with the error that you have just obtained, and then another term that is built considering a little bit of lead. I mean, look here, the term V at iteration E plus 1 is equal to the term V at iteration I plus the error at iteration I, and of course this is okay, but at time or at step k plus 1. So we are a little bit looking into the future. Yes, but we are looking into the future of the previous iteration. So you can do that. This is important because the iterative learning control gives you an opportunity that no other controller can give you. That is using also future data, but the previous iteration. This is very good because thanks to this approach, they could demonstrate easily that the evolution of the error that here is expressed like a discrete transfer function can goes to 0, and this is a contraction map if the closed loop function has all the poles inside the unit circle that is possible choosing the opportunely the matrix F, and then choosing also a matrix G in the right way, you can have that all the eigenvalues of this matrix are inside again the unit circle, and so this can be a contraction mapping. But this is may happen only because you are considering one step in advance the error. This is a technique that will be used also later. Just to be complete, I have to tell you that sometimes you may try not to consider all the memory that you have from the previous iteration, but just a part of it. Using a term, a multiplicative term that is called forgetting factor. Forgetting factor because you forget a part of the previous input. Is it working? Well, yes and no. Yes, because the convergence is easier. Yes, because maybe you have the opportunity to forget disturbances that are not periodic, I mean, non-persistent. So disturbances that you could not reject with an iterative scheme, but the convergence is slower, and then you cannot guarantee an exact tracking, because you never reach exactly the input that you need to have a desired trajectory. But, of course, you may go very, very near. Then there are a lot of people that try to reason not in the time or with the samples, but directly with frequency. So using transfer functions. For example, in this paper, well, I think that this is the right paper, but I'm sorry, I cannot be sure, because I found many references to this paper. I know more or less what is written inside, but I have lost the original paper, and I don't have. So I must put a question mark in this citation. I'm not really sure, but should be that. In any case, they propose an iterative scheme in which the input U is updated, multiplying the error for a constant alpha. A, not alpha, A. This is possible, of course, so you consider only a part of the error. And working with transfer function, you can demonstrate easily that if the plant is proper and is stable, and the Nyquist plot of the plant lies entirely in this circle, then that is the inverse is stable again, then this updating law is stable. more important maybe is the law that has been found and proposed by Ulivi with Poloni in 91 and with De Luca in 92. This is a very complete law. I like very much because it does two things with a single shot, let's say. There is a multiplication factor, a transfer function alpha, that is multiplying the error, and another function, transfer function, beta, that is multiplying the previous input. So you can do two things. First, using beta, you can select the frequencies at which you want that the controller must keep zero error. So you may have a beta that is equal to 1 until a certain frequency and then goes down. And second, using alpha, you can stabilize the loop. I mean, the iterative loop, and because of the convergence rule is given by this expression here, in which alpha should be the exact inverse of G, it is possible if G, that is the plant, is not as for example, non-minimum phase zeros, it is possible to use a transfer function that inverting G is non-causal. It is possible, of course. Why it is possible? Because you can always implement, this is the problem, because you have a transfer function that is not causal, but then you have to implement in the time. But you can implement using the samples of the previous iteration that you have, because you have all the samples of the previous iteration. So you are allowed to use also non-causal gains. In this way, you do the two things. You choose which are the frequencies that you want to in which you want to the error near to zero or zero, and you may have non-causal inversion. This is a very, very nice result, of course. A similar result is due also to Kevin Lee Moore. It's very similar. I put this slide only because Kevin Lee Moore wrote a large number of papers on iterative learning control, and I want to remember him. I think that he produced also the very first survey on iterative learning control at the end of the 90s. So it was very important, very active in this field. What about time-varying plans? Now we start with things that are a little bit more complicated, but not so much, because always in 1985, Kawamura, Miyazaki, and Arimoto, always the same people, demonstrated that even if you have a plant that is time varying, the important is that it is repeating in the same way all the time. So at each iteration, it's varying always in the same way. Okay, if you have such plant, you may set up a learning algorithm, in this case, in this paper, using the error, not the derivative, but the error directly. And you may have very easily the convergence of these algorithm. Another approach presented by Moore with time-varying plans is this one. This one is quite different, because in this case, yes, you have an update that depends on the output of the system, but you directly multiply the output of the system by the inverse of the plant. And the inverse of the plant is obtained with an optimization problem. So you calculate the minimum at each iteration, of course, of this expression with respect to n. Then when you have the minimum, n is exactly inverting the plant, and then you may apply it to update the input. This is a real data-driven scheme. In which you don't have a model. You estimate everything at every iteration. Of course, there are other kind of formulations. For example, you can put in one vector all the samples of the input. You can put in one vector all the samples of the output, and then you can write the system considering an expression in which you have a matrix G that is just mapping the inputs in the outputs. This is a very compact, of course, representation, but it is compact in the sense that you write easily, but your matrix G is very large, of course, because there are all the numbers of your system inside. And this, I think that in the 19th, this was considered not easy to use, but actually I think that is exactly what we do in data-driven control. So this is no more a problem. There are many papers, of course, that are based on this representation and presents results that more or less say the same things that we have seen. What about nonlinear systems? Okay, when we go to nonlinear system, we have to imagine that there are several techniques that have been presented in the years, using, for example, Lipschitz analysis, or partial feedback linearization, or maybe you may decompose your system in several different controllers using, for example, backstepping techniques, or you can use sliding mode just to constrain your system on particular manifold or particular trajectories, or you can use singular perturbation analysis, trying to linearize as much as possible your system, or you can use any other kind of stabilizing controller just to transform your nonlinear system in something that can have better properties and that can fulfill the conditions that have been found and published in several papers. But also looking to the paper of Arimoto in 1984, we found that there is also an approach to nonlinear system. The nonlinearity is limited to the function f. So we suppose that the input is linearly related to the derivative of the state, and the output is linearly dependent from the state. So the nonlinearity is just limited to this part of the system. Well, simply supposing that the function f is Lipschitzian, and of course there are hypotheses on continuously differentiables of some of the input of the output, and then considering this condition here that is similar to the one that we have seen before, they were able to demonstrate again the convergence of the derivative of the error to 0. This demonstration is quite simple. And then at this point we have to remember all the work that has been done in Italy by Giuseppe Casalino, that in 1984, so the same year of Arimoto, proposed a scheme related, of course, to a robotic application, in which there is a linear computer torque. That means you imagine to have an input that is made mainly by a computer torque or something that is related to the trajectory that you want to implement. But there is also a part of the control that you can modify at each iteration. So at the very end, what you're doing is just updating your computer torque, adding the term that wants to compensate the difference between what you estimated from the beginning and what you really had to give to your robot. The condition for the convergence of this scheme is not difficult to satisfy for a robot, as you see, and so this was a successful scheme that has been applied many times. Of course, I'm speaking of a work of 1984, and so in the last 40 years have been done many other things, many other approaches that are working on feedback linearization. Backstepping is also another possibility. You can use, for example, you have a system, a nonlinear system for which you have an output that is related only to one state variable. You close one loop using a virtual reference, then you close another loop, and then you may define a learning scheme that can be used to stabilize the external loop, let's say, propagating the effects inside towards all the other controllers that are part of your decomposition. More easy to do than to explain. I found also this very interesting paper, and this paper is really recent. It's 2023, and it's due to Pierallini, Angelini, Mengacci, Alleschi, Bicchi, and Garabini, in which they consider this very interesting application under actuated system with elastic joints. So a real difficult plant. The model is here, it's a nonlinear model, of course, and then elasticity adds many difficulties, of course. You may have also, they consider having also non-repetitive disturbances. And they also consider the problem of having non-repetitive bounded deviation of the initial position. So they imagine that also the initial position is not exactly always the same, but maybe it's near the same position. They consider a law in which they update the input with a time and iteration dependent gain. So they try to do something really not easy, but in spite of such difficulties, they are able to calculate the evolution of the error iteration by iteration. The expression is here. They have to consider the Lie derivatives of the function h of the output, of course, and then working also with conditions more or less related also to Lipschitzian constraints. They are able to demonstrate that the error remains bounded. I think that it's enough. It's the most you can do, because you are supposing non-repetitive disturbances. So more than this is really impossible. Another interesting paper that I found, I couldn't write the year, but it's recent, is the control of cranes. Cranes are difficult to control because you have a mass that is suspended behind another one that can move, a trolley that can move along a bridge, and typically these are non-minimum phase systems, and in this case the authors propose to use sliding mode. So they firstly define a sliding surface, or more than two sliding surfaces, and they close the loop with this sliding mode. After closing the loop with this sliding mode, so after reducing the system to a behavior that is really simpler than the one that you have without the sliding mode, because without the sliding mode you have a lot of equations, nonlinear, very difficult to use. Then you try to update a contribution that iteration after iteration is related, of course, to the output of their system, and they succeeded. In this paper, they clearly show how this approach can be feasible. And if I remember, there are also some experiments just to show that is really feasible. Which are other problems related to iterative learning control? At this point, there are a lot of problems, also new problems. One is the problem that I cited before, for example, for non-minimum phase systems for which you have, for example, robots with elastic elements, and non-minimum phase system have the problem that when you go to invert the plant, the inversion is not stable. This means that if you want to control them with a standard feedback controller, the only thing that you obtain is instability. We have already seen that this kind of problems in iterative learning control can be overcome using non-causal inversion, or that means, for example, using a transfer function filter that is not causal, or in schemes for which you don't have transfer function but you have the samples, considering advanced output data, or even it is possible to consider a shift of the reference. So advancing the reference is more or less the same that shift the output data. This is a possible solution, but remain in any case some problems, because the convergence sometimes is really problematic. Another problem that is incredibly difficult to solve is the problem that you have when your trial is not ending. For example, you are trying to learn something a little bit difficult, and your system cannot complete the trial because it is collapsing before. For example, you would like to learn how to play with a ball, and at the very beginning the ball falls down. So you are not able to complete a trial, so what can you learn? Okay, there is someone in particular, there is this paper of Dongshan Kuefang Li that is called Iterative Learning Control for System with Iteration Varying Trial Lengths, 2019, in which they make a nice analysis of all the problems that you may have with trials that are not ending. They propose to consider a modified tracking error that is very simply put to 0 for the samples that you don't have. Then, using a particular operator that is an iteration average operator, they propose a modified iterative learning control scheme that you may read here, and they demonstrate that there is the possibility that this algorithm can achieve convergence, even if the trials at the beginning are not completed. So there are a lot of people that are working on this topic, and I think that there are a lot of possible applications. Another problem that is a big one is the initial state shift. I mean, the state at the very beginning, it is possible that it's not always the same, because you are not able to put the system exactly in the same state at the beginning of your trial. What does it mean? This means that you have a kind of persistent term that if it is always the same, you can try to compensate iteratively. But if it is changing iteration by iteration, you will be never able to compensate it. What you can do, for example, you may try to not consider the error at the very beginning, multiplying it for a function that initially is almost 0 and then later maybe became equal to 1. So you try not to consider the errors at the beginning, hoping that the transitory that is connected to the initial condition will vanish, and so it is not so important. Then you may try also to, there are some proposals of modifying the reference. So considering a different reference that take care about this, the problem of having an initial condition that is not always the same. Or sometimes you may add an initial phase in which, starting from another condition, you try to reach the condition, the initial condition that you need. This is possible. Well, this is necessary when the initial state is known, but is not the correct one. What does it mean? That there is no initial state shift, but the initial state is not good for the trajectory, for the output trajectory that you want to obtain with your system. This happens practically every time you want to move a flexible robot, and a robot with flexible elements, and if you want to go from a position from rest to rest, so straight to straight, you would like to follow for the tip a particular trajectory, but you know that this trajectory is unfeasible unless you start with an initial deflection. That has been demonstrated in many papers. So the internal state is not the correct one, and you have no possibility to achieve the trajectory. But what you can do, you can try to change the initial condition. So just use an initial phase in which you change the initial condition, then you start with the trajectory. Another big problem is related to data that are not always available. But why? For many reasons. For example, you are using an incremental encoder that is giving to you data only in some simple time that are not enough for the application that you would like to implement. I mean, the sampling time of the encoder could be slower than the sampling time of your algorithm or the encoder or any other kind of sensor. So you don't have all the samples that you need. Or you are on a network and you lose some packets, or you are in a networked system and you lose some packets, or packets are coming with a delay. In any case, this is a problem that is called intermittent data, and it is possible to work with intermittent data in some conditions. There is an interesting paper of 2022 of this Nerd Strichbosch and Tom Omen, I don't know the exact pronunciation, and that has been published on Automatica, Iterative Learning Control for Intermittently Sampled Data, Monotonic Convergence Design and Applications. Interesting paper you must read if you want to know something about this. Another thing that we have to say is that not always iterative learning control is done on trajectories. So there are some applications in which maybe you don't need to follow exactly a trajectory, but you just want to reposition or steer the state of your system from one initial state to one final state. This is called iterative state steering, and of course has a dimensionality that is lesser than before. And it can be done very easily, and most of the time has also less problems than iterative learning control. It's not difficult to set up such algorithms. You may imagine that you have a linear system, then of course with a linear system you have a linear mapping between the control input and the final value of your state. It is a linear mapping. It is of course a convolution, so it is not easy to manage, but it's a linear mapping. And this linear mapping can be used to represent the final state in function of your input in this way. So this is the initial state, this is the contribution of the input, and this is the final state. Okay, if you set a control law for which you update your input multiplying the error between the desired final state and the actual final state, multiplying by an operator f, multiplied considering an operator f, you just with a very simple substitution, you may obtain an iteration for the error that is described by this equation. And of course, if f is able to invert exactly the operator n, you obtain ek minus ek. So you obtain 0 from this equation. You have the convergence only in one step. Otherwise, it is possible that you don't have exact inversion, and so considering the norm of such operators, if the norm of this expression is less than 1, okay, you may have, in any case, a convergence of the error to 0. Okay. This is something really very complicated if you consider it in this way. But don't forget that if you want to steer the state of a system, and this system has a state, for example, of dimension 4, you don't need 40 parameters, or you don't need to compute something with a high dimensionality. You just need 4 degrees of freedom. You may need only 4 parameters to do that. This means that you may imagine to define your input as a linear combination of base functions. Base function can be, for example, polynomials, but not only. You are not limited to polynomials, but for example can be polynomial. So you have a linear combination of base functions with parameter alpha. And so when you go to write the relation between the parameters alpha and the final state, you obtain only a matrix. A matrix, so the operator is a mapping represented only by a matrix. So you multiply this mapping for the parameters, you obtain the final state. At this point, you can easily use this mapping to update the vector of parameters. And the relation that you have at the very end is should be this one. I think no. No, yes. It's this one, and it's very easy that demonstrate the convergence of this algorithm. And the good news is that any kind of problem related, for example, to non-minimum phase system have no importance for this algorithm, because you're not considering the transfer functions or all the output along the time, but you're just considering the final state. So this works perfectly also with system non-minimum phase. This is, for example, an application that we have done in 97, Lucibello, Panzieri, Olivi, in 97, with flexible robot arms. You go from this position to this other position. This is the value of the first angle. This is the value of the second angle, and this is the deflection, I think. No, these are the speed. The deflection is here, of course. There is a small deflection at the beginning, then the robot is deflected in the other sense, then it stops. So it's very easy to implement if you don't care of what is happening between the initial state and the final state. You don't control it. But really, you cannot control. No, you can control, because if you want, you can put several intermediate steps and say that you want particular outputs at such steps. Of course, you have to increment the dimension, the number of your parameters, but you always have a controller that has a low dimension. That is very good. The same reasoning can be applied also, for example, to non-holonomic robots. This is a paper in which we apply this algorithm to a car-like robot. And you know that it is possible for car-likes to transform the model into a chained form, but the chained form has the property that the first input is related to the first variable in this way. So Z1 dot is equal to V1. The second input is related to the second variable in this way, and the equation of the other variables are dependent only from the first input. So if the first input is, for example, piecewise constant, the second part of your system is a linear system as far as the input V1 is constant. And so if you decide to use basic function make as a constant for V1, you have a sequence of linear systems. So you have something that is time varying, but it is constant for some intervals, for many intervals, and so you can set up this learning algorithm very easily. And this is the application that I told you before. That is the steering of a flexible arm, rest to rest. This is the trajectory of the tip. It is linear. So we ask it to the tip to go from this point to this other point, but because of it is not possible to start to have this trajectory unless you have an initial deflection. This is the graphic of the deflection. You need an initial part in which you make a state steering just to reach the right initial position for the deflection to have the right trajectory tracking for your system. I got 3 more slides, so I promise I finish very soon. One is this one. Iterative feedback tuning. This is a very interesting iterative scheme, learning scheme, in which you consider that your system is controlled by 2 transfer functions that are depending from a parameter rho, and you update at each iteration this parameter, optimizing, let's say, optimizing this objective function that is the expected value of the error. So you make an optimization. Every iteration you make an optimization, and after minimizing this objective function, you have a new value of, you have the possibility to update the value of your parameters in using a quasi-Newton method. That is, the problem is to compute a gradient, but the gradient is not easy to compute because you have to calculate in some way. Or now calculating this gradient is possible only doing some experiments. So this is an iterative scheme that use the experiments also to evaluate the gradient that will be used to update the parameters of your controllers. It seems quite difficult, but it is possible to apply. There is this very nice paper on IEEE control system that shows how to do that. Another extension that I want to show you is this one. It is called cyclic control, in which you have state steering that is done cyclically. So this is not a cyclic trajectory. This is just, we are just asking to the system to have some particular values for the state in some points. And then from one point and the successive one, you may have any kind of trajectory. But it is interesting that the update of along these cyclic trajectories take place without stopping the system. So while the system is cycling, you may update with all the samples that you are collecting while it is going around. This also is very nice. Maybe it is possible to say that one very similar to iterative learning control is repetitive control. In repetitive control, you have something that is called a periodic generator that is done in this way. In synthesis, this is just a delay of n samples. So this loop can memorize a sequence of n samples. You can put here, and this element continues to learn and contribute to the control. So it is a memory, so continues to contribute to the control until this error goes to 0. This is an important scheme that has been used in many cases. In particular, in this paper, we use this repetitive controller to make the velocity, the rotational velocity of a wind turbine as much stable as possible, trying to compensate for variations that are mainly due to the fact that the wind in a wind turbine, a large wind turbine, is not the same when you go down or when you go up. I mean, there is an effect that is called wind shear, that is also terrible for airplanes that are landing. And so the velocity of the wind is less when you go near the ground. And this difference of velocity of the wind induces vibrations and variations of the speed of the rotation. But you have a control action that acts on the inclination, the rotation of the blades, so you can change the incident angle of each single shade. You may try to compensate in this way the effect of wind. Of course, the controller is repetitive because it continues to rotate as far the wind is coming. Last slide. I found this paper of 2024, very nice, but maybe we are at the very beginning of something new, in which an explainable AI, I don't know if you know what an explainable AI is, substantially is an AI to which you ask to explain what is doing, and you connect this AI almost to everything, and then you ask to this AI to put in relation all the things that sees with a new value for the contribution that is given to the iterative learning control. So during each iteration, the system applies the current control input, measures the resulting output, and computes the error between the desired and actual outputs. The control input is then updated based on this error using a predefined learning rate, and until now it's always the same. But you can use this shapely additive explanation that is a typical scheme of explainable AI. You can use this SHAP to provide insights into the influence of different factors on the control decision. SHAPs are made just to judge how different terms of an expression may influence a particular output. So you can use, for example, to understand a particular cost function made of different terms, which is the term that is more influent. Okay, in this case, SHAP is used to judge about the influence of the error output or the input or any other terms who is connected, and can be used to better understand the evolution of the iterative learning control. Okay, I don't think that it is really the future, but I think it's something that we will see in the future more and more. I don't know. Okay. I think this was the last slide, so I can thanks everyone to be here and for the attention that they gave to me. Thank you very much.
Thank you so much, Stefano. Thank you for your interesting presentation. It was really insightful, and you guided us through a long story and long path in this iterative learning control. And so it's time now to give the opportunity to the audience to make some questions or any curiosity regarding the iterative learning control in this talk. Is there any question from the audience? I will start with a short question and then give the time to the audience to think about there. The first thing that goes into my mind when you were talking about this iterative learning control, that is, in fact, some sort of data-driven control. Do you think that there is space for the combination of iterative learning control with machine learning, so that some forms of hybrid control of ILC and machine learning based methods can be developed to improve eventually some features that are limitation of ILC?
In my opinion, thank you for the question, Graziano. In my opinion, there is space for iterative learning control almost everywhere, because it is something that is going to improve a previous controller. So if you have a good controller that has some good performance, but you want to try to improve because your controller maybe is not able to absorb a periodic disturbance that you maybe you don't know enough. Don't forget that in periodic tasks, of course, adding a memory of n samples means to add to your controller a system with n states. So something that for the internal model principle is able to contrast, let's say, or to reject an error, a disturbance that again is made of n samples and different and independent samples. So it is a easy way to enlarge the capability of your controllers. Maybe your controllers is a transfer function with 10 parameters, but your trial is made of 1,000 samples. You may have the memory of 1,000 samples, and suddenly you have the possibility of doing something that your previous function was not able to do. So I think that can improve. Machine learning and iterative learning control, I think that, I don't know if they are compatible, because machine learning works in a way that is able to learn maybe the dynamics of a plant. this is possible. And so it is possible maybe to use it just to have an inversion of your plant. An inversion of the plant is useful because you need to have a stable iterative learning controller. I don't know. I don't think that there are many applications of this together with iterative learning control. I don't know if there was another question from you.
From me, yes, but let's give time to the audience if there is anybody else that wants to make a question.
I mean something that I've not answered.
No, for me it's okay. It was exactly the question that I was posing to you. And another type of curiosity, this is more related to the application of this kind of control. You showed us the wind turbine application that is really interesting as a topic, a kind of problem. And on which kind of other applications you think that there could be space for this kind of iterative learning control?
Maybe I have an answer, but I've seen also Alessandro De Luca here that opened his microphone. And maybe if I can, I answer later to your question.
Yeah, sure, absolutely. Please.
Yes, can you hear me?
Yes.
Yes.
Okay. So thanks, Stefano. It's been a long time for me not working on this topic. And in fact, we did work together many years ago, too many probably. But in your presentation, you mentioned something. So I would like to see if I understood it clearly or if you have done some work on that area. So you were mentioning in particular the cases of non-minimum phase systems, in, let's say, a flexible arm. And yes. You said that the problem here arises when you're trying to track an output trajectory, an output which is non-minimum phase. And in that case, we know that if you have the model, the solution may be non-causal, so you have to start applying an input which starts before the start of the trajectory, and when the trajectory vanishes at the end, you have to still apply for some time a control so that the system returns to rest. Whereas if you don't follow a trajectory, you just need to do a rest-to-rest motion, for instance, for the same system, then you can find a solution, I mean, when you have the model, that it's limited to the time of the desired motion. So if you want to make a rest-to-rest motion in 3 seconds, you have a command that starts at 0 and ends at time 3. So my question is the following. When you're trying to capture the non-causal part, so the part of the control which starts before the trajectory and the one that ends after the trajectory has finished, can you just apply those techniques that you made, or have you done this by extending the interval of learning? So instead of going from 0 to capital T, you go from minus delta to capital T plus delta.
I don't know if you have seen this slide.
Maybe I missed something, but so
this is the paper of '97 that I did with Pasquale Lucibello.
Okay.
In which I did exactly what you're saying. We did exactly what you're saying, in the sense that the problem is going from rest to rest with a linear trajectory for the tip. But this cannot be realized unless you start with a deflection. Okay. And to reach the deflection, you extend the learning time on the left here of 1 second, during which you make a repositioning. So you apply something that put you exactly with a deflection that you need to have exactly the tip trajectory you need.
Okay, but does this, fine, but does this part modify just the internal state without touching the output? So the output is not moving?
No, the output is moving, look.
And this is my question. I would like to have a command that does not move the output, because the output will move only at time 0 and should stay there at final time t, while you're actually applying a command which is in some null space of the output, which modifies the internal state without moving the output. This is my question.
I don't know if I have the answer. I don't know if it is possible. Thank you for the very interesting question.
It's like exploring the zero dynamics. So you live in the zero dynamics, but you modify the state inside the zero dynamic until you start.
So you need to limit your input to something that is exciting only the zero dynamics.
The zero dynamics without, remaining in the submanifold of the zero dynamics.
So you move in the intersection, you move in the controllability subspace. Without going outside the unobservability subspace. So you should find the trajectory inside the intersection between the controllability and unobservability subspace. Maybe can exist for some system.
Maybe there are conditions under which you can do it. Sometimes you cannot do that.
I will be back to you in 1 month.
Okay, good. And the second comment, more general, related to, and then I will stop, and then related to the last topic of machine learning integrated to these techniques. I mean, with some students, we made some times ago a comparison. What happens if you have a single trajectory to be learned and you apply this type of technique for standard, let's say, rigid robots, so no problem with non-minimum phase. Or if you try to just apply reinforcement learning on multiple trajectories, and then you see what happens on that particular trajectory. So my feeling was that if you have to do a very good tracking of a single trajectory, still this method beats the machine learning technique. Whereas as soon as you want to generalize, of course, here you have to restart from scratch, while with what you have learned in machine learning, it's reasonably good also for the new trajectories. So what is your experience on that?
The problem with machine learning is that you don't know why, but it is functioning. that is, you can accept to start from scratch anytime, because you are not doing that. It's doing my computer on my desk while I'm going to the bar. The generalization, you mean how much good could be the generalization of a neural network when you pass from one trajectory to another one? Because the problem at every learning control is that you learn how to realize one single trajectory. Every time, only one. And you have a memory that is good for that trajectory. I was asking to myself, but if I do that exactly for n different trajectories with n iterative learning controllers, then I give the results to one neural network, and I ask to that, okay, can you generalize this result? This is interesting.
Or maybe the reverse. So you do the training in the usual way, and you have reasonably good starting point for any trajectory. But then, can you at this point take the output of your neural net and do some refinement on that specific trajectory? Because it's a matter of accuracy that you get.
Of course, you can have a generalization that is not exact, but then it's a good starting point from an iterative learning controller. Yes, because we know that having a good starting point helps. At least you have to do less iterations on your real system. That don't forget that not all the systems are robots. I mean, there are a lot of systems on which you cannot do trajectories and experiments, very large one. I mean, in industries there are. So if you have a good guess, then maybe with some little refinement, eventually, while you are working with your normal cycle, I mean, you are on production, and then you go on production because your neural network gave you a good solution. Then you are on production and you try to update a little bit just to have less vibrations or a better performance in tracking or something like that.
Okay, thanks.
Thank you, Alessandra.
So thank you all. And I think that with this last part and interesting question, we can close our lecture. Thank you again, Stefano, for your interesting talk. And we will meet again on May with our next lecture. Laura, if you want to say something and conclude.
Yes, thank you, Stefano, and also Alessandro. You asked many things, and some of them were in my mind, so I am not repeating anything. And in my mind, I had I was trying to understand the difference between adaptive control and iterative control, but then I understood that. Mainly iterative control is when your task is repetitive, like in a robot, you can do the same experiment many times, while in adaptive control, this is not the case. And maybe this is also the difference with machine learning that is more similar to adaptive control. Anyway, thank you, everybody, and we will see next lecture that up to now is in May. Maybe there will be another in April, but we will let you know. Okay, thank you again.
Thank you very much. Bye. See you.
Bye. Bye.
And sorry, Stefano, we will put the recording on our YouTube channel, so we need your permission for that.
Yes, of course you have.
Okay, bye.
Thank you. Bye.
Bye. Bye.